Hello, this screencast is a walkthrough through two of the items from Chapter 8 for Week 9 on sampling and probability. The first item we're going to walk through is item number 8.13, which focuses on using random numbers in the table to help us assign subjects into different groups as needed in a research study. So in the back of the book on page 470, it's called Table H, Random Numbers, is a sheet that just has computer, random digits generated by a computer that were then printed on this textbook. Every textbook has, usually every stats text has a set of random digits in the back of the book in a table, or you can use online sources. There are plenty of online sources if you had to conduct some type of research and assign subjects into different groups in a random way. So I'm going to walk through how you would use this table, and they also then have posed some questions here of whether or not the method they propose for each item is an acceptable method of using this the random numbers. So what I did here was I went down to row 7. I just picked row 7 myself. So 0007, the first 5 digits here on our table are not actually randomly generated. These are actually just indicating which row you're in. So these are not going to be of use to us once we've selected this row. And what I have here is to the right, these are the digits that are written out in this row. These spaces are simply just spaces so that you can keep track when you're actually using these. There's nothing more than that. It's just a visual representation to help you to not lose track. If these digits were all crunched together, it makes it pretty difficult keeping track, with your eyes. So I wrote out a few of the numbers here that are generated randomly. And the question is, for example, if we wanted to assign subjects to group A if the random number is even and group B if the random number is odd. This is supposing that we have two groups, group A and group B, and we want subjects to be randomly selected or randomly assigned into those groups. And if we want to have equally likely chances of a subject being assigned to group A versus group B, then we need to use these tables in a manner that the numbers themselves have equally likely chances of being either group A or group B. So since even and odd are split up 50-50, half of the digits are even and half of them are odd, and 0 we do count as an even number, then this would be an acceptable way to randomly assign individuals. So for example, the first individual you might assign the number 8. And the number 8 here is an even number. So therefore the first person or subject, whether it's people or whatnot, the first subject then would be assigned even or group A. And then the next one here is a 5. So since 5's odd, then that would be assigned group B. The next item is number 2. So that digit then assigns that next subject to group A. And then the next one is a 6. So therefore then that would also be assigned group A. And then 9 is odd, so that would be group B, and so on. They ask if, for letter B here, if you assign 0 through 4 or 5 through 9, meaning if the digit is 0, 1, 2, 3, or 4, then they get assigned group A. And if 5 through 9, meaning 5, 6, 7, 8, 9, if they are then the number generated, then that would go to group B. As long as these are equally split, there's actually 5 digits here between 0 and 4 inclusively, and 5 of them here between 5 and 9. So this would work. However, if you take a look at item C, they ask with 00 to 40 or 41 through 99, would this be a good way to allocate with even chances, equal chances going to either group A or group B? This would not be a situation where you would do that. Because there's actually 41 digits here between 00 and 40. Think about if you're reading a book and there was a page 00, and then a page 1 and a page 2, it would actually be 41 pages reading here. And then from 41 to 99, that would be more than 41 right here. But I want to point out in question D, they propose 000 to 499 and 500 to 999. And one question that comes up often is, how would you possibly use these numbers and these random number generated tables here to what on earth is going on here? So this means that if, for example, I select 3 digits, the first 3 digits here being 852. 852 falls in the category of between 500 and 999. So since these first 3 digits fall into this category, then they would be allocated to group B. The next 3 digits would be 697. You notice here I just took the next 3 digits in a row. Those also would be from group B. And then the next 3 digits, 760. Those would allocate here to group B. And then the next 3 digits, 202, they fall between 000 and 499. And therefore then this would indicate the next subject would be assigned to group A. The next one here is 051. Another good point here. Notice the 0 here. It doesn't mean to skip that to go 516. It means 051 is an actual number, and that means that it falls between 000 and 499. So therefore, if the next subject was assigned 051, then they would be placed in group A. So hopefully that helps explain how to use the random digits here for 8.13. Now let's take a look at 8.14. 8.14 says that the probability of a boy being born equals 0.5 or 1/2, as does the probability of a girl being born. So for a randomly selected family with 2 children, what's the probability that, and then they lead that off to then go on to the next 3 questions. So our premise here is that we have a randomly selected family with 2 children, and we want to take a look at what are the various probabilities of their outcomes. So I set up here a tree diagram, which I believe helps tremendously in both organization and grasping all the different possible outcomes. So if the first child, so what I did here was I set up a tree diagram as if we're taking a look at all the probabilities for each birth. So for the first birth or for the first child, the text is saying that it's a 50% chance or 1/2 probability of it being a boy and 1/2 chance of being a girl. And then after that first child is born, the second child it's what are called mutually exclusive events and also independent events. So the second child has it does not matter whether the first child was a boy or a girl as far as the probabilities for the second child. So if the first child is a boy, then there's a 1/2 probability that the second one is a boy and a 1/2 probability that the second one is a girl. Or if the first child was a girl, after that, the probability that the next child is a boy is 1/2, and then probability that the next child is a girl is 1/2. And what this does is, if we follow each of these different trees, each of the different paths, then it gives us the 4 possible outcomes here. Meaning, we could have the outcome of having a boy and a boy, or a boy and a girl, or a girl then a boy, or a girl and a girl. So we have a sample space here of 4 different possible outcomes. And the probabilities assigned to these are as such. So if the probability that the first child is a boy is 1/2, and the probability that the second child is a boy is 1/2, and these are independent events, then I multiply the 2 1/2s to get 1/4 to give us the probability that both children are boys. So that gives us the probability here of 1/4. And that answers question A, which says, what's the probability that that a randomly selected family that has 2 children has 2 boys? And the answer then would be 1/4 or 0.25. Remember, when you're converting the decimals, there has to be between 0 and 1. You can't have a probability higher than 1 or a negative probability. The next question then says, what's the probability that there are two girls? So we're going to follow the flow here, or the tree diagram of girl, girl, which means we have a girl and a girl. So the first girl's probability is a half. The second child is a probability of 1/2 being a girl also. They are independent events, so we multiply them together to get a probability of 1/4. That answers part B then, 1/4 or 0.25. Now let's go on to item C. It says either two boys or two girls. Now, since it's either two boys or two girls, we are satisfied if we randomly select a family that has two boys, like this group, or two girls, like this group. And since selecting one family and having either two boys or two girls are mutually exclusive, which means it's impossible to get both scenarios with the same one pick, then we can add these probabilities together, 1/4 plus 1/4, to get 2/4, or 0.5 as the probability that, again, you randomly select a family that has two children and neither both are boys or both are girls. There's one question floating out there that was not asked, but I'd like to pose it, is this: if there was a letter D, I would pose, what's the probability that they have one boy and one girl, and they don't care about the order? Well, if that's the case, then there's two ways you can do it. You can either, one, take a look at the fact that in the middle here I have boy, girl, and girl, boy. Both of these are 1/4, so I'm going to add them up to also get 2/4. Or you can use the fact that all four of these are all the possible outcomes. These four probabilities, whenever you do this with tree diagrams, whenever you have all of the possible outcomes listed, those probabilities must add up to 1, because one of these outcomes has to happen. And therefore, if I add them all up, it should encompass all of the possible outcomes. It's certain that one of these four things is going to happen. And if I know that the probability of having either all boys or all girls is 1/2, then the probability of not having all of the same sex, which means you have a mix, boy, girl, and girl, boy, has to be the remaining part. So I can take the 1/2 from the answer here in part C and subtract it from 1 to get the probability also of 1/2 that there is either a boy and a girl in the family. So hopefully that helps with this. 8.14 leads right up to 8.15. You can just continue this tree diagram to one more child. So off of this, you're going to get branches for another boy and a girl, another boy and a girl, and so on. Thank you.